an explanation or apology. I'm going to tell you how this particular program came about. The theme of this European school has been esoteric codes, right?
Yeah.
And right now, codes are very popular in the world because of a novel. A picture has been made called the Da Vinci Code. Now, I had not read the Da Vinci Code, but I thought since I was coming to this school, which is about codes, and the Da Vinci Code has been so popular, I had better read it. So I sat down and read it. I don't really care much for the writing of Dan Brown, who's the author of that book, but I plowed through it. And partway through the book, I discovered that a very important element of that story is something called the Fibonacci sequence. In fact, the Fibonacci sequence is a key element in that book. And for those of you who have not read the book, I just made a pun, because the Fibonacci sequence is connected with a literal key in the story, and it is a key element to resolving a mystery in the story. Now, as it happens, I have long been interested in the Fibonacci sequence and in something else called the golden ratio, which is connected with the Fibonacci sequence. So I started thinking about those things and wondering how they could be represented visually, because they are two mathematical concepts. So this talk is going to be about mathematics. Now, if you are a mathematical phobe, if you don't like mathematics and it turns you off and you go to sleep, I am going to do my best not to increase your somnolence, your sleepiness. The program is entitled The Golden Ratio, the Fibonacci Sequence, and Numinous Numbers. Does anybody know what numinous means? Numinous means pertaining to the inner reality behind outer appearances. So I think there is an inner reality behind the outer appearances of the golden ratio and the Fibonacci sequence. Now, the golden ratio is also appropriate to this meeting because it was first discovered or first described by a Greek geometrician. So let's have a look at these things and see how they go. We're going to try to whiz around them. Now, this slide is mathematical. So if you really hate mathematics, close your eyes, and I'll tell you when we get to the next slide, which is no longer quite so mathematical. We're going to start with the golden ratio. What is the golden ratio? Well, the golden ratio is a proportion between two sizes that is held to be the most aesthetic and pleasing of all proportions. It's a matter of art, in fact. And it is defined by the golden section. So what is the golden section? Well, a definition of it is that the golden section is the division of a line into two unequal segments, such that the ratio of the whole line to the longer segment is the same as the ratio of the longer segment to the shorter segment. Now that's all perfectly clear, isn't it? Let me try to clarify it. Here we have a line, AB, right? And if we divide that line at this point, point C, we've got two segments, which are of different lengths. If the ratio of the whole line to the longer line, the longer segment, is the same as the ratio of the longer segment to the shorter segment, that is the golden ratio. Or, if we put this mathematically, if we divide AB by AC, the result will be equivalent to the number we get if we divide AC by CB. That figure is called the golden ratio, and the name for it is the name of a Greek letter, phi. Not pi. Everybody knows pi, don't you? Remember pi from mathematics? It had to do with the circumference and the area of a circle. Well, phi is different. Phi is the golden ratio. It's what you get in this proportion. It is, in fact, a number which is called irrational. Irrational numbers are decimals which have no end. They are infinite. It begins 1.6180339888749, and you go on forever, right? And that makes your head spin. What is the significance of an irrational number? A number which has no end. Well, I would suggest that the numinous meaning of that, the inner meaning of it, is something which we read in Light on the Path. And I've referred to this passage once before. Light on the Path says, "For within you is the light of the world, the only light that can be shed upon the path. If you are unable to perceive it within you, it is useless to look for it elsewhere. It is beyond you, because when you reach it, you have lost yourself. It is unattainable, because it forever recedes. You will enter the light, but you will never touch the flame." Why is it that you will never touch the flame? Because the search for self-discovery has no end, because the self has no end. The great self is infinite, so we can never reach the end of it. So the search is unlimited. And that's what the irrational number, the infinite number, really means. And is such a number. Now, phi, or the golden ratio, was first developed or stated by Euclid, the great geometrician. Euclid wrote a book called The Elements, and that book was the standard textbook for geometry for 2 millennia, and it is still the basis for beginning geometry. An extraordinary important Greek mathematician. He did all sorts of things. One of the things he did was to state the Pythagorean theorem. We won't go into that, but he also talked about the Platonic solids, and we'll discuss these a little bit later, and he also talked about all of the properties of triangles. Very important things. He was a genius. You know, since we are here in Athens, let me point out the obvious. Western culture is Greek in origin, right? Greek philosophy, Greek art, Greek literature is the basis of Western culture. It got modified by some other things, but it is the seed from which all Western culture grew, and it's enormously important. And Euclid's contribution was commemorated by a poet by the name of Edna St. Vincent Millay, and this is the poem. Euclid alone has looked on beauty bare. Let all who prate of beauty hold their peace, and lay them prone upon the earth, and cease to ponder on themselves while they stare at nothing, intricately drawn nowhere in shapes of shifting lineage. Let geese gabble and hiss, but heroes seek release from dusty bondage into luminous air. O blinding hour, O holy, terrible day, when first the shaft into his vision shone of light anatomized. Euclid alone has looked on beauty there. Fortunate they who, though once only, and then but far away, have heard her massive sandal set on stone. The facts of geometry are beauty bare. They are the basis of our perception of those archetypal realities. All right, now, we talked about the golden ratio, and we said that it was that infinite number, but we called phi, but we usually identify it simply by its first four numerals, 1.618. And then it goes on and on and on. Now, using that golden ratio, one can construct something called a golden rectangle. And a golden rectangle is like this. It is a rectangle whose height, let us say, is 1, and then to that one adds, and that's, this part of the base is the same as the height, right? If we have a square there, and this part of the base is 0.618, and so the whole length of the base of the rectangle is 1.618, etc., on and on and on. Now, the golden rectangle is an extremely interesting figure because if you take off a square, what you have over here is another rectangle, and that rectangle is a golden rectangle itself. And the golden rectangle is said to be the most pleasant, pleasing shape around. And that's been tested. Psychologists have given people a bunch of different rectangles. Rectangles are simply four-sided figures, right? A bunch of different rectangles, and said, which of these do you like best? And the choice centers on the golden rectangle. So people do respond to it as being their favorite shape. Now, that golden rectangle appears all over. It appears in nature, it appears in art, it appears in architecture. And we're going to look at some specific examples of the golden rectangle in a moment. I think I'm not going to go into how to make a golden rectangle. It's quite simple, but I think we can skip it for our purposes. That's what that diagram shows. But again, let me emphasize that the golden rectangle is such that it consists of a square plus another golden rectangle. Is that much clearer? That's all we need to know at the present time. All right. What's this a picture of?
Of
Of the Parthenon. Right. The Parthenon, if you make a rectangle around it, is guess what?
Golden.
A golden rectangle. So the facade of the Parthenon is a golden rectangle. And that means that, as in this diagram, you have to sort of reconstruct the top of the Parthenon, which has been lost. You've got a square, and you have another golden rectangle here on the right. And you can keep on going down that way. Golden rectangles exist inside golden rectangles. So here we have a golden rectangle, and don't worry about what those numbers mean. For the time being, they are only to identify parts of this. This part 21 is a square, and what we have over here is another golden rectangle. If we consider that part which is over here, down here, it's got a square in it, and what's added onto that square is another golden rectangle. And if we take that golden rectangle and we divide off a square from it, what's left over here is another golden rectangle. And that goes on, right? We keep analyzing it down and down and down, and what we have is an infinite number of golden rectangles. And of course we can build it up the other way too, right? Can't we? We could take this golden rectangle and construct a square on top of it, and the whole figure would be a golden rectangle. Now that is also highly symbolic. What is it that what is it that the Emerald Tablet says? As above, so below, as below, so above. There is, throughout manifestation, correspondences. And that's what we've got in the golden rectangle. Don't you think that's interesting?
Fascinating.
Just as an abstract fact. As a numinous bit of numbers. All right. I showed you this mural from the Masonic Grand Lodge of California the other day when we were talking about Freemasonry. What I didn't tell you then was that it's constructed of golden rectangles. Basically, what is right here in the center is a golden rectangle. All right? Furthermore, the great French architect Le Corbusier was fascinated with the golden rectangle and the golden ratio. And he developed something which he called le modular. And he did this because he thought that buildings ought to be constructed in accordance with the human anatomy. Because buildings are constructed for human beings, and they ought to be livable. And if they're going to be livable, then they have to match the human anatomy. And Le Corbusier thought that we could find the golden ratio in the human anatomy. So if you take a typical human being and you start at the navel and you divide him into two halves by the navel, and if we say that the top is 1, then the bottom is 1.618, etc. The human being shows the golden ratio in our proportions. And furthermore, you can keep dividing. You take the upper part of us and divide the upper part of the neck, you get exactly the same thing, the golden ratio. And if you take the bottom part and divide it at the knee, you get the same thing, Le Corbusier said, the golden rectangle. Now, in fact, that works pretty well. Michelangelo's David, I have put here beside a picture of a human being with divided according to Le Corbusier's golden ratio proportions. And in fact, that's the way we are. So the human body demonstrates the golden ratio. Now, obviously, we're at different heights, and there are individual variations, but that's like saying that the average Eskimo family consists of 4.5 members. It's an average, and that's what the golden ratio is in the human anatomy. Now, the golden ratio is also very important in the pentagram, or the star, right? We've talked a little bit about pentagrams or stars. If we take a star, doesn't make any difference what size it is, if you take the dimension, the length of one of the points of the star as 1, then what will be the dimension of the base here, the space between two of the arms of the star? Guess what it is? 0.618, etc. It's the golden ratio. And this works, or 5. This is all the way through. Every dimension in a pentagram is either 1.618, or it's 0.618, or it's 1. So the golden ratio defines the relative size of all parts of a pentagram. And not only of a pentagram, but pentagrams are connected with triangles. Because if we have a pentagram, like this one, inside a pentagon, right, you get some triangles, don't you? And those triangles are called golden triangles, because they also have the proportions of 5. And there are two kinds of them. There are acute triangles and there are obtuse triangles, depending on whether it's a triangle with a narrow point or a triangle with a broad point. Both of them are golden triangles because in both of them what you have are the proportions of phi, of the golden ratio. Don't you think that's remarkable, really? Just, where does all of this come from? Euclid alone has looked on beauty bare. That's what Edna St. Vincent Millay meant, right? He discovered these wonderful correspondences between geometrical figures. And not only do we have triangles in the pentagram here and here, we've also got one here, a big one, right? A big obtuse one. And for that matter, we have right here an acute one. And all of these are golden triangles. The proportions of the sides of the triangle are phi, or the golden ratio. The pentagon, the pentacle is very important as a symbol of humanity. The five-pointed star is a symbol of you and me. And that was recognized quite early by a fellow named Agrippa, who was a very early Renaissance philosopher. And he produced this design which shows a human being as a kind of pentacle. And we see it also in Raphael's painting The Crucifixion, which art people have analyzed as having a triangular and a pentagonal design in them. And the two, of course, overlap. And the Platonic solids are interesting things, because the Platonic solids, these were mentioned by Plato, described by Euclid. They are the five basic three-dimensional figures. They are regular three-dimensional figures in that all of their sides are equal, are the same. So that one of them, for example, is the cube, which consists of 6 squares. Right? And another is this, which consists of 4 triangles, and this has 8 triangles, and this one has 20 triangles, and this one has 12 pentagrams. But they're all, with except of the cube, triangles and pentagrams, and they are all involved with the, and you can put them inside one another, build them inside one another, and they all are involved with the golden ratio. And the golden ratio is even involved with the pyramids. This is the Great Pyramid of Giza. And in it, if one takes a point at the center of the base of the pyramid out to the edge of the pyramid, and if you take that as 1, then obviously the whole base is 2, right? So this is half of the whole base, and the diagonal going up the side of the pyramid is phi, 1.618, etc. And the height of the pyramid is the square root of phi. Perfectly remarkable. All right. One gets in Rembrandt's self-portrait, again, a triangle which is very close to a golden triangle. And here is a painting by Seurat, the French painter who's a pointillist. You know, all of his paintings were made with little dots which he put on. This particular one is called La Parade du Cirque, the circus parade. And art critics have pointed out that this whole painting is a golden rectangle. And furthermore, it consists of a square and another golden rectangle. and there are golden rectangles throughout this painting. Seurat didn't do that accidentally. He knew it. You don't do that sort of thing accidentally. This was intentional. And here is another example, again by Seurat, called The Bathers. And the whole thing is a golden rectangle, and it can be divided, as we see here, into squares and golden rectangles, and it's got golden rectangles which are involved in the various figures of the painting. Seurat was fascinated with the golden rectangle. And here's a famous painting by Salvador Dali of the Last Supper, and it shows Christ and the apostles at an altar, and what is the shape of the altar? It's a golden rectangle. Now you're seeing it in perspective, of course, but it's a golden rectangle. And what is it we have here in the background? One of those platonic solids? Exactly. And so Dali, too, was concerned with the golden proportion. All right, now let's move from the golden ratio to the Fibonacci numbers, which is what got me started on this. Fibonacci was a remarkable Italian mathematician who lived from the late 12th century to the middle of the 13th century. Before Fibonacci's time, numbers were written with Roman numerals. You all know Roman numerals, made of 1s and V's and X's and C's and D's, right, and that sort of thing. Fibonacci, and these are just different portraits of Fibonacci. Fibonacci wrote a book in which he introduced what we call Arabic numerals. I say we call because they were not actually Arabic at all. Arabic numerals come from India. They're really Hindu numerals. The Arabs learned them from the Indians, and Fibonacci learned them from the Arabs. But those numbers are remarkably important, because if I ask you, would you please add 2,431 to 1,509, you have no trouble doing that. You write the two figures down, one above the other, and you simply add them, right? 9 plus 1 is 10, so you put down a 0 and carry a 1. And the one you have carried in 3 is 4. And then 4 and 5 is 9. And 2 and 1 is 3, right? Addition is simple with Arabic or Hindu numbers. How about addition with Roman numerals? Would you please add MMCD, XXXI, and MDIX? How do you add those two together and come up with MMMCMXL? And addition is relatively easy in Roman numerals. Try long division with Roman numerals. I can remember when I was a very young child, we used to play with Roman numerals, and I read how you can do long division with Roman numerals, but it takes page after page after page of written computation to get the answer. Fibonacci was, in one sense, the greatest mathematician Europe has ever had, because he introduced Arabic numerals and the decimal place system that goes with them. Now, Fibonacci also propounded a problem, a very famous problem, which is called the rabbit problem. And the rabbit problem is basically this. Fibonacci gave this problem. A certain man had a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that original pair in 1 year if it is supposed that every month each pair begets a new pair, which from the second month on itself reproduces? here's the Fibonacci problem illustrated. We start with a pair of rabbits in January. Now, they can't reproduce the first month because they've just been born. They have to be, they can only reproduce in the second month, all right? They don't reach sexual maturity until the second month. So the second month, that pair of rabbits produces a new pair of rabbits. So by March, we've got the original pair plus the new pair. In April, we've still got the original pair, and they have reproduced again, because they can reproduce every month. The rabbits are very philoprogenitive, which means they just like to reproduce. And the second pair, the first pair they produced, still exists, but they haven't reproduced yet, because they have to be 2 months old before they can do so. By May, the first pair still exists. The pair which they reproduced earlier still exists, but not yet. And the first pair has produced a new pair. And meanwhile, that original pair they produced has reached sexual maturity and has reproduced. So in January we had one pair. In February we still only had one pair. In March we had 2 pairs. In April we had 3 pairs. And in May we had 5 pairs. Now notice, what is the relationship between those numbers? That is the Fibonacci sequence. 1 plus 1 equals what? 2. 1 plus 2 equals what? 3. 2 plus 3 equals what? 5. So by June, how many pairs of rabbits are there going to be? 8. By June 8, July 13, August 21, September 34, October 55, November 89, and December 144, which is rather nice because December is the 12th month, 144 is the square of 12. But that's just an accident, I think. All right, that's the Fibonacci sequence. Fibonacci sequence is any sequence of numbers such that you add the 2 adjacent pairs of numbers and you get the next number in the sequence. Well, that may just seem like, you know, a sort of a trick, an interesting phenomenon. But in fact, it is related to the golden ratio. How? Well, suppose, here's the Fibonacci sequence, right? Carried on. We've just seen it. 1, 1, 2, 3, 5, 8, 3, 21, 34, 55, 89, 144. Then if you add 144 and 89, what do you get? 233. If you add 144 and 233, what will you get? 377 and onward. And this too is an infinite sequence, right? It has no end. So it's just like the golden ratio in that way. But more important, instead of adding any 2 sequences of numbers together, suppose we divide a number by the preceding number. If we divide 1 by 1, what will we get? 1, right? 1 divided by 1 is 1. You remember that from division, don't you? And then if we divide 2 by 1, what will we get? 2 by 1 is 2. And then if we divide 3 by 2, what will we get? 1.5. And then if we divide 5 by 3 and so on all the way through, I'm not going through these, we're going to do them quickly, right? We get these numbers. I've gotten all the way up here to 160 divided by 987 divided by 610. Now look at these results, please. Do you see anything in them which is of interest? Where have we arrived at the end? 1.618. Does that remind you of anything? What is that? That is close to the golden ratio, right? And notice what has happened is that we are constantly, in this process of division, approaching 5. The first division is way below it. The second division is above it. The second is still below it, but not quite so far below. The fourth division is above it, but not so far above it. And each division, we get closer and closer to 5. Do we ever reach 5? Why not? Because phi is an infinite number. And we go on dividing the Fibonacci numbers of the Fibonacci sequence, and we get closer to phi with every division, but we never reach it. Why? You may enter the light, but you will never touch the flame. It's the same thing. The golden ratio to the 50th decimal place is that, and notice we have gotten, with this division, that far. We keep on dividing Fibonacci numbers, and we will get closer and closer to this infinite number, but we can never reach it. All right, now, what is the relationship between the golden rectangle and Fibonacci numbers? Remember I told you those numbers, we were just going to use them to identify? Oh, they have another purpose. Let's start with the two inmost squares here. 1 and 1. If you add 1 and 1, what do you get? 2. If you add 2 and 1, what do you get? If you add 3 and 1 and 1, what do you get? If you add 5 and 1 and 2, what do you get? 8. If you add 8 and 2 and 3, what do you get? 13, right? If you add 13 and 3 and 5, what do you get? 21. 1, 1, 2, 3, 5, 8, 13, 21. What are those? Those are numbers of the Fibonacci sequence, the beginning of the Fibonacci sequence. Right? So the golden ratio and the Fibonacci sequence are equivalent. Right? And furthermore, that is the basis for what is called the golden spiral. If you begin right here at the center with the 1, and you make a spiral going around like this, that's the result, right? Do you all see that? I begin here, and I go around making a spiral, hitting the corners and all, and that is actually a picture of a salamander's tail. It's a reality from nature, and that tail is a golden spiral, because it is defined by a sequence of golden rectangles. And it's not just that. This is a seashell. It's the kind of seashell which is called a chambered nautilus. And it is a spiral, and that spiral is a golden spiral.
It's the cover of my book.
Okay? The golden spiral is defined by golden rectangles. Right? It occurs in nature, not something invented. So the golden ratio and the Fibonacci sequence are not just abstractions. They are followed by nature. They are objectified and manifested in natural forms. Euclid alone has looked on Beauty Bear. Beauty Bear is the archetypal reality which is manifested by seashells and by salamanders' tails. And we get the Fibonacci numbers also in floral life. That is to say, now this is just a drawing, but we are told that the natural form of branching of a plant is first from 1 to 2, and then from 2 to 3, and then from 3 to 5, and from 5 to 8, and what do we have there? The Fibonacci sequence. So plants branch according to the Fibonacci sequence. It is in nature. And plants like these, which have a spiral construction, their spirals are golden spirals. That is to say, you could plot them onto the golden rectangle. And here's just a flower. And how many petals are there in this flower? I'll tell you, there are 13. Flowers tend to, the number of petals on a flower tend to be numbers in the Fibonacci sequence. Roses have 5. Is that in the Fibonacci sequence? Yes. All flower petal numbers tend to be numbers from the Fibonacci sequence. And then, of course, people have always been fascinated by this. This is a photograph of a building in Göteborg. And what do we have painted on the side of the building? 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, etc. And what are those? It's the Fibonacci sequence. Why did somebody paint the Fibonacci sequence on the side of a building? I have no idea. But it fascinates people because it is this abstract numerical sequence which manifests itself in natural forms. Hence showing that the inner side is like the outer side. The outer side is like the inner side. We have our correspondences. And here's another example. This is a British chamber ensemble, a popular British chamber ensemble, and they call themselves the Fibonacci sequence. Why? I have no idea, except that the Fibonacci sequence is a fascinating thing. And we can also do poems. Rather recently, people have begun writing what they call fib poems. And fib is short for Fibonacci. And a fib poem is a kind of Western haiku. You all familiar with haiku, the Japanese poems that are defined by the number of syllables in each line? Well, a Fibonacci poem is one with whose lines consist of a number of syllables which are in the Fibonacci sequence. For example, here's a fib poem. One small, precise, poetic, spiraling mixture. Math plus poetry equals the fib. Notice the first line is not there. Why? Because the first number in the Fibonacci sequence is 0. Fibonacci sequence begins with 0, 1. And that itself is powerful because all of computer technology is based on 1 and 0. The computer talks to itself solely in combinations of 1 and 0. My daughter worked for a computer company for a long while, and she was dealing with what are called compiler languages. And the compiler language is what the computer uses to talk to itself, all 1s and 0s. She got bored with that. First line is not there because it's 0, but then 1 syllable, small, 1 syllable, precise, 2 syllables, poetic, 3 syllables, spiraling mixture, 5 syllable, math plus poetry yields the fib, 8 syllables. So you can do a fib poem like that. Here is another fib poem. My life is a plethora of more things to do than there are minutes in the day. And still another fib poem. Math makes my head quake with pain. Writing a poem based on Fibonacci does the same. Now, most Fibonacci poems are only, 6 lines long, or 7 counting the line which isn't there, right? And that's a lovely length, because 7 is very symbolical, but also because if you go beyond that, what happens to the length of the lines? They become very long indeed. Here is a Fibonacci poem which is longer. What is a fib? A poem mathematical. Syllables are arranged in lines, according to Fibonacci's sequence of numbers. 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and... As it happens, the numbers 1 through 89 contain exactly 21 syllables, which is what you need, which is a Fibonacci number, which you need for that point. Now, in addition to these Fibonacci poems, all of which I took off the web, there's a great, there's a group on the web, on the internet, that are devoted to writing and exchanging fib poems. They're very popular. But in addition to these, I have composed 2 fib poems myself. And these are theosophical fib poems. Oh, all right. I'm sorry we have these little circle 2s. That should be 0 with a line through it. All right, naught, null, right? Because the first line isn't there, which is very theosophical, right? You begin with nothing, and then the next line is 1, and this is like the operas that Harold was talking about the other night, where you get the 1 beat, and then 2 beat, Fibonacci sequence, right? Okay, nil, naught, something suddenly comes out of the dark, growing toward the crescent light. And here's another theosophical poem, which I call When and Where. Now, here, always, everywhere, not any time, nor any place upon the earth. Now, I urge you all to go out and write some fib poems. They are great fun to do, right? So what you need, and stick to 6-line fib poems, right? 1, 1, 2, 3, 5, 8. And see what you can do. Express yourself artistically with the Fibonacci sequence. All right, now here's the last, I think, maybe not, we'll see. What have we got on the screen?
Circle.
A circle. And circles are also, numerically, zeros, right? And that's the beginning of the Fibonacci sequence, isn't it? Zeros. But just to make sure you know that, we'll put a 0 atop. And now we will produce the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. The beginning of the Fibonacci sequence. And what do we get if we take the numbers, any 2 numbers in the Fibonacci sequence, and divide the second by the first? What will we get? We get the golden ratio, or phi. And so phi is at the heart of the Fibonacci sequence. May the phi be with you. May all your ratios be golden. May your fibbing never stop. May you enter the light. And that's the end. About anything. I used to tell my students, you can ask your question about anything in the universe. I do not guarantee to give you an answer. Anything at all? Yes.
Correct me if I'm wrong. Is it, I thought I read somewhere years ago that in Indian numerology the 0 didn't exist. Is that correct?
Yeah, that's right. The 0 was introduced by Fibonacci. It's part of the Arabic numerals. It's part of the Indian numerals. The ancient European culture, classical European culture, had no 0. Right? There's no 0 in the system of Roman numerals. And the lack of a 0, the lack of nothing, makes mathematics extremely difficult to do. In order to do mathematics easily, you have to have nothing. You have to have a 0. That's part of the decimal system. Quite right. So the discovery of nothing was an extremely important one in the history of Western culture, which we imported from India by way of the Arabs. Anything else? Yes, sir.
So if anyone's interested, he's actually buried in the church opposite the leading tower of Pisa.
Pisa. Okay, very good. Yeah, I think Fibonacci was from Pisa, as I recall. So that would make sense. There's someone we don't know about, but extraordinarily important in European culture.
So, from my point of view, John, it's not that nature is actually reflecting the Fibonacci series. It's that the Fibonacci numbers are describing what is seen in nature.
Of course, yes, yes. What we have in nature is an actual physical manifestation of something. And the Fibonacci numbers and the golden ratio are an abstract description of that pattern which we find in nature. Now, you can argue about whether nature exists first and we abstract from it, or whether the abstraction exists as bare beauty, which then is reflected in nature. Plato would give the second explanation. Plato would say that the abstractions are there, the ideas are there, and that nature is the shadow of those ideas, that they are real and nature is a copy of it. But for you and me, we find it in nature and then we abstract it from nature, right? But of course, which view is right? The answer is don't ask silly questions. Both views are right. It just depends on how you happen to look at it. That's just like the question of, does the earth move around the sun or does the sun move around the earth? Now, in early days, everybody knew that the earth was stable and the sun moved around it. Today, we know that the sun is stable and the earth moves around it. Which is correct? Don't ask silly questions. It depends upon what your viewpoint. You have to take a viewpoint of something. You have to say that something is stable and you're viewing everything else from it. Neither the earth nor the sun are stable. Both are moving. And how they are moving depends on where you look from. So the ancients were not foolish. They simply took a different viewpoint from the viewpoint we typically take.
Well, I just wanted to put a slightly different slant on that, John.
Please.
And say that nothing can exist until it's an idea. Manifestation is from above downwards, we say in Theosophy, don't we?
Right. Of course. We're Platonic. Theosophists, generally speaking, are Platonic.
But the idea is a mathematical idea and also a thing.
That's fine. Oh, you're quite right. It's not a thing. Things belong in the physical world.
Right, absolutely.
The question is, which is more real, ideas or things? And there, it depends upon your viewpoint. Don't ask silly questions.
Wasn't there a Greek philosopher who said God geometrizes?
Yes, of course.
Who was it?
It was probably Plato, as a matter of fact.
Oh,
Pythagoras. Okay, very good, Pythagoras. Yes, it's a well-known saying. It comes out of the ancient world. All right?
It's
Yes.
interesting that Pythagorean math was more fluid, more related to waveforms, less static in a way than Plato's. I call it a living geometry. And there are now physicists who are showing how the geometrical forms derive from each other, and when you can make this look like flowering and see it in motion as a
fractal
living
geometry.
geometry. The toroidal form that keeps turning itself inside out, and the flower that grows and all that is a living geometry. That makes it, I think, more palatable to those of us who see a difference between mechanism and organism. It's the bridge for me, the living geometry.
I think, the real moral of all this is to be tolerant of different views. It's, I think, always a mistake to say, this is the way it is. Everything is only as we see it. And we will see it according to what our basic assumptions are, according to our standpoint. So you can see the same thing in different ways, depending on the point from which you view it. So I think this discussion is very useful because it's pointing out that fact. And no viewpoint is wrong. They are just different.
And John, the other thing is you can take any number, you can start with any number and any other number. Choose any two numbers you like, and then by adding them and using the same, you'll still get the golden ratio.
Absolutely, you get the Fibonacci sequence. You get the start of the Fibonacci
It's the
sequence.
same law.
Oh yeah, universal law. It's a fascinating thing. Okay. Well, thank you all very much for your tolerance. And have a good evening.